This is a report on MATLAB exercise number 3, transfer function exercises. So, first of all, I have switched from the usual script in MATLAB to a live script. This is because by using the live script, you can the unnecessary use of the prefix function in favor of the display feature, which is inline in this case for MATLAB. You can also change it from inline. You can also do it to output on the right, or you can hide the code. But I will do it on inline. That way, for every code afterwards, the result is shown. So, for example, here we can see what is the main uh, matrix. This is the matrix for the whole equations. And so by using the det function, you can find its determinant, and this is the determinant. Okay. Next, when it comes to solving the equations, so here we have is the equation for the delta 2. Okay. The first thing we have to do is find the I2, which is again the determinant of this matrix that defines the I2 all over the determinant of the whole matrix, which is this one. And so we get that our I2, although it was hidden by the use of this semicolon, so if we unhide it, this is what it will look like. But even by hiding it, you can also hover on I2 itself, and it will display right below what it is expressed to. So by using the circuit or by analyzing the circuit, we can see that in order to get our VO in some way, we have to use a Ohm's law at the 1 over 3 farad capacitor. So you will have to do a VI minus VO is equal to I2 times 1 over 3, or rather 1 all over 1 over 3 S. So instead of doing that, what we can do is we can first express the first equation as one equation, so equation 1. So I use this notation for that, and MATLAB automatically assigns that as equation 1. So as you can see, I did not define what is I2 yet. That's because it is this one. But it automatically replaced I2 here with the result here on the top. Next, for equation 2, we can define h, which is our transfer function, as VO over VI. And so, by using the solve command, so what is the solve command? So solve command simply solves any equation that was given to it as an array. So equation 1, equation 2 here. And on the next array is all the variables involved. So in our case, we involve the VI variable, the VO variable, and the TF variable, since they are all unknown in the equations. S doesn't have to be assigned because it is assigned already in the Sims S. So we are simply using the VI and VO for the transfer function. And this is all the documentation about the solver. I also even provided the return conditions equals true because you have to, as per here, the return conditions true returns if you will call your result. So let's call the result. You can see that there are 3, or rather 5 different variables, and you even have the conditions. So if you will have result with that conditions, it will provide all that conditions itself. On the other hand, if you look for the TF, you can go and type result.tf, and you can see that there are 2 results. So this first one relates to the first equation, which is equation 1, meaning there was no TF in that first equation. In the second equation, however, there is the TF, and thus you can actually call it here. You can even call result.vi to see that here in the first one, this is what it is, and on the second one, the Z. So by using the collect command to simply only collect your result for TF2. So the collect command simply extracts a part of the answer of one command. In our case, our command actually has multiple results. So the collect will only collect one specific output that we require, which is again in the TF. So using the simplified TF, because again, by using TF, this is still not yet simplified. So using the simplified TF, we arrive at this following transfer function. So for our second part, we can use here. So since it requires that you find ZO and ZI, you find ZO from the all the resistances connected from VO to VI. So this is what we know as the external resistance or external impedance. So the external impedance can be calculated from that by simply applying the series and parallel equations. So this is your external impedance. For your internal impedance, it's from VI up to the ground because this defines the input. So it does not require that you also calculate the impedance from the input to output. Okay, only here in the input directly to ground. And so with that, you arrive at this answer. So we can now define our equation 1 and equation 2. Our equation 1 will be our op-amp equations using ideal op-amp conditions, and our equation 2 again is for the transfer function. So using the solver again, we find that this here is our transfer function. So we can now use those transfer functions to find their step responses and the periodic responses. So we'll go with the step response for the first transfer function using the h is equals to v over vi by finding the Laplace of phi d of t, which again is 5 over s. You can see here that we can find the Laplace of vi. The Laplace, sorry. So the Laplace is 5 over s. Okay, we multiply that to the transfer function defined here, and then we apply our inverse Laplace, and this will arrive in this inverse Laplace equation in terms of t. On the other hand, if we use it on the transfer function of that op amp, we arrive at this answer, and that goes for the rest as well. So in conclusion, we have successfully used symbolic math to obtain transfer functions. But in addition to some symbolic math, we also have incorporated solver, which allows us to solve equations both as a matrix and as regular expressions easier in comparison to simply manually importing it ourselves. As for the circuits, we saw that the first circuit involving various uh, L's, L, R, and C produced questionable results for the response, especially if it is still only like a type of step response. And the op-amp equations, we have saw that it results in a appearance of that original response. If it was responding with, if you input a sign as a response, it will reproduce a function that also has that response as sign. So that concludes the report.